And hopefully that's the end of the lectures in next week. So we'll see what happens. Okay, so my little thing where I kind of say, well, kind of a throwaway in the first 5 minutes. So good old Ashby, I've mentioned, and Michael Ashby is a real leader in materials selection and design, and he's a great material scientist, okay? And I'm not going to try to knock him for that. We'll knock him for something else, okay? But I got to find here. So Ashby, I showed you probably on the first day of class, second day of class, this Ashby plot of materials used through the ages. I certainly showed it several times. And it turns out I was wrong. I went back to some of his books. I thought this was one of his 1980 books. It was actually the Material Selection and Mechanical Design, and he actually came up with this plot. First I could find it was 1992. He does have books going back to 1980, but didn't have that plot. So here's the plot, and that's where my slide came from. Whoop, what'd I do? You know, it did this to me earlier, before everybody got here. I think there's something wrong with this cable. Let's try. Well, that's not working. Not the cable. This is on. Reboot that. Well, okay. I hit a button somewhere, and then I hit it again, and it works. Anyway, Ashby came up with this plot in 1992, and what he said, well, anyway, So this is the first edition of this material selection and mechanical design. And then the fourth edition, that was 1992. The fourth edition is 2011. So I sort of, when I presented this, I said, well, you know, he was extrapolating around 1980 or 1990 and saying, oh, the amount of metals is decreasing and it's going to continue to decrease, and the amount of other structural materials is going to increase over time. And so I just happened to buy this a week ago, and I was flipping through it. And what he says in the fourth edition is he sort of corrects that, okay? And he says in the caption of this thing, now he's got it in color, I'm going to have to get it in color. He says, the evolution of engineering materials with time, relative importance, which he's plotting on the vertical axis there, okay, of the materials, which is what he had before, is based on information contained in the references. Okay, from 1960 onward, so from here onward, data for teaching hours allocated to each material family at the United Kingdom and U.S. universities, okay? So this is basically, and it's true, you know, when I was a student in 1970, it was a metallurgy curriculum. It was metallurgy and material science. And it didn't become material science and engineering until 1974, okay? Or 73 or something, anyway, in this department. And so it was primarily metallurgy, and that's correct. Except that's not what he said in 1992. In 1992, that plot was supposedly, here's the plot, okay? And he says the evolution of engineering materials. This evolution and increasing pace are illustrated in figure 1.1. The materials of prehistory, blah, blah, blah. Okay, up here. There had, of course, been developments in other classes of material, Portland cement, refractories, and he's talking about the fact that everybody taught metallurgy back in the 1960s. The rate of development of new metallic alloys is now slow. Demand for steel and cast iron has actually fallen. That's wrong. It has never fallen. Oh, maybe in 1 year, but if you draw a trend line over a decade, it's been increasing, okay, and it continues to increase. Okay, the polymer and composite industries, on the other hand, are growing rapidly. Yeah, because they were so small. It's not hard to grow rapidly when you're small. It's very difficult to grow rapidly when you're big. Okay, it's what your baseline is. And projections of growth of production of new high-performance ceramics suggest rapid expansion here also. Well, this is right after the ceramics fever. You know, they're going to make jet engines out of ceramics and all this other stuff. Hey, you're supposed to be the material property guy. You're supposed to know about strength and toughness. Okay, you got the plots in your book. Well, in fact, he was on the same type of bandwagon as everyone else in 1990, saying, oh, metallurgy is dead. Okay, the last department head in this department was a polymer guy. He actually said metallurgy was dead, which I didn't particularly appreciate. But nonetheless, other materials are important, and I'm going to talk about some of those. Does anybody have any questions? Sorry about the several minutes I killed trying to get this thing operating. No questions on this? Well, this one's not looking very good. I got to get these things out of these things. I had a long time ago, I gave a talk on material selection at some conference. If you look at different materials, there's got to be a better way to get this. Let me try it with the light. Okay, well, that's not so bad with the light. Okay, material and the strength to density ratio. Well, it turns out aluminum is better than steel for typical strengths and densities. Composites are right in there, equal to steel. Very fancy composites can actually be significantly above, but we're talking about materials that cost $10,000 a pound. Plastics are relatively low, even though they're the lightest weight of all these, as is wood. But it turns out if I'm going to build something like an aircraft, you look at the strength to density, which is the specific weight of the material. We make aircraft out of all these things. I mean, one of the biggest aircraft ever built, what do they call Howard Hughes's, the Guppy or whatever? The Spruce Goose. Yeah, the Spruce Goose was made out of wood, okay? So in the 1940s, when you wanted to make the biggest aircraft in the world, you didn't make it out of aluminum, you made it out of spruce. Okay, they only built one of them, but anyway. But it worked, okay? So there is, again, there's competition for materials. Now, another thing from that same talk that I gave, selection of structural materials, well, the number one thing I've been telling you is cost, okay? Strength and fracture resistance, there's your strength toughness, and that's what I've been saying is, after cost, that's what we're worried about. And we really didn't worry about fracture resistance until the last 25 to 50 years, and some industries haven't even caught up yet. Availability, okay? One of the strengths of steel is there's a lot of iron out there, okay? And it's not hard to come by. That's the strength of aluminum. It's just that aluminum takes a lot of energy. But they're both available, and that's why they're the two most common metals. Wood, really good quality wood, we're running into the same type of problem they had back in the 1500s in England. They're really good big trees and high quality trees. They're sort of been, we've deforested them and we don't have them like we used to. And so people are using composites and making things look like fake wood and stuff. Fabricability. Hey, if you can't machine it or cut it, you can't weld it very easily. It's one of the problems with ceramics. I showed you the ad for the watch, and the little bezel. Well, you know, the ceramic is very difficult to machine. Yeah, well, that's why you got to buy a $40,000 watch to have them make it out of ceramic, right? Recyclability. Now, that's an interesting topic in and of itself, in that I told you the most used metal is steel, at 1 billion tons a year, and steel is about 80 to 90% recycled, okay? Everybody thinks of recycling of aluminum. You know, people go around and pick up beer cans and soda cans and recycle them. Aluminum is like 50, 60% recycled. It's not as recycled, it's not recycled as much as steel. And there's a number of reasons. It turns out the aluminum alloys are so different in their classes that you try to mix them all together and you end up with a mishmash that you can't use for much of anything. And so people are working on new ways to separate the alloy content out of the aluminum alloys. But steel is the most recycled, but there's two materials that are much higher than steel in usage. Does anybody remember what they were? They're not metals. Stone and cement. And well, wood is there too. You don't recycle. I mean, you go to the hobby shop and Ken Stone recycles wood. Okay, he made some things for me, and it all came from recycled wood. Okay, he used to use the old MIT we had desks like this, and they were solid cast iron legs, and it was bird's eye maple. I mean, it's beautiful maple, 2 inches thick, solid. Okay, yeah, we got rid of them rather than refinish them. It's beautiful wood. So Ken's got some, I mean, he recycles that. And anyway, so he recycles wood, but mostly wood is kind of consumed. It's a renewable resource. But recyclability, the one that we make 1.5 billion tons a year of that we don't recycle is cement. And you can't keep putting 1.5 billion tons a year of big old rocks, because once you break it up and you have an earthquake or you go destroy the building and send it to a landfill, you can't keep landfilling 1.5 billion tons a year. You want a problem to work on? Figure out how to recycle cement. There's a huge industry out there, and at some point in the next 10 or 15 years, people are going to realize you can't keep landfilling all the cement. Okay? We've had a tremendous growth in the use of cement. You know, it used to be 500 million tons. At 1.5 billion tons and continuing to grow, particularly in the third world, you can't just keep building up piles of old rubble. Repairability. This is one of the Achilles heels of all your fancy composites. Okay? How do you repair them? Okay? You went to all this trouble and processing and extra expense to make this fancy material, and you have a hard time. So there are also others. I mean, this is just what I put up at that time. I actually have a list of 10 or 12 different things, and you can think about some of these things in terms of specific examples. However, even Rudyard Kipling knew that gold, oops, gotta drop it down in size. Rudyard Kipling, gold is for the mistress, silver for the maid, copper for the craftsman cutting at his trade. Good, said the baron sitting in his hall, but iron, cold iron, is master of them all. So this is what I've been telling you is not something new. It's been known for a long time. Okay, I want to start kind of a new topic now, but before I do that, our theme before was there are practical limits on toughness and density. I told you, hey, for penetrators or for little, eyelids for people who have been disfigured, density is important. Toughness is important, and I could teach a whole class on the problems of toughness, where we had a brittle fracture in something. This is something that I wrote up before on nails. We already went through nails. I'm not going to go through nails again and the growth of importance of steel and nails and stuff. Ashby points out that the ages of the human race are defined in terms of the materials that they use. There's the Stone Age, the Bronze Age, the Iron Age, and now some people say we're in the Silicon Age, so far as that goes. We used the materials that were available. The Romans used stone and concrete and built ships of wood. The civil engineers here have a concrete canoe contest every year where they try to make a concrete canoe out of chicken wire and concrete. Okay, you don't usually think of concrete as a material for ships, but hey, if you don't have to use it for very long. And I've talked to you about the materials that we use. It turns out that the topic I want to switch into, which is not necessarily a material selection, but I kind of lecture like I feel like, and that's productivity. And I thought I'd tell you a little bit about Made in America. This book, Regaining the Productive Edge. Okay, Michael Dertouzos, who Michael is a professor, he was running the computer science lab at MIT. Richard Lester, is he now head of the nuclear engineering department? Anyway, he's been an administrator around here for 20 years. And Bob Solow is an economics Nobel Prize winner. And so this is the MIT Commission on Industrial Productivity. Now, I actually, as a younger faculty member, got involved in this. It started about 1985 at a meeting in the School of Engineering conference room. This was published in 1989. And at the time, in the mid-'80s, the Japanese were knocking our socks off in manufacturing. And everybody thought that the problem was regaining the productive edge. Well, in 1984 and 85, I went over to Japan. And I watched, I was over there for a year on sabbatical working for the U.S. Office of Naval Research. And it turns out, I looked at things, I was visiting research labs and manufacturing facilities all over Japan for a whole year, and I said, this is not better than what we have in the United States. It might have been making better quality, but at the time there was a significant competitiveness issue, and that was that it was 250 yen to the dollar. After World War II, it had been like 350 yen to the dollar or something. Today, anybody know what the exchange rate is? It's about 100 yen or 90 yen to the dollar. Okay? Well, back in 1985 when I was there, 250 yen to the dollar, I mean, a 10,000 yen note was a $40 bill. Okay? And yeah, my housing was pretty expensive. The U.S. government paid $36,000 for me to rent a house in Tokyo for my family. And food was expensive, particularly if you wanted to eat like an American. If you want to eat like an American in Tokyo, really expensive. I mean, back then, 1985, a box of Cheerios could cost you $15. Okay, that'd be like $35 or $40 today. Hey, because they had to import it from the United States. If you wanted to eat like a Japanese, you could eat pretty cheap. And if you wanted to eat like Chinese, you could eat really cheap in Japan. I had a certain advantage. I was a U.S. government employee for that year, and I could go out to the post exchange, and I could buy things at the military exchange, and they would have C-5As coming over from Seattle on the weekend. You go out to Yokota Air Force Base, and there'd be 10 of them there. And this is the National Guard, basically taking a $250,000 flight from Seattle to Tokyo to get their training time in. Okay? And what were they offloading? Big pallets of Coca-Cola. So I could buy a case of Coke in Tokyo cheaper than I could in Boston. Okay? And it had been flown across by the military. Okay? So there's all kinds of competitiveness things there. And I remember when I was first there, the first week I was there, I showed up at church and they said, can you go, I was the only person who was a government employee at the time, can you go down to the embassy and buy us hot dogs? Because they were going to have a social, and they wanted like 300 hot dogs, and a hot dog in Japan would cost you like $2 a piece just for the hot dog without the bun. I go down to the commissary and buy it for 50 cents a pound, okay, for hot dogs. So I had to go down to the commissary and buy all these frozen hot dogs that week. But there's some disparities. One thing I learned, if you're ever going to live abroad, live under the U.S. State Department rules. Those people know how to live abroad, okay? Obviously. They take care of themselves. Anyway, so we thought that the Japanese were these master manufacturers, and it never quite made sense to me in the mid-'80s from what I'd seen over there. They had lots of inefficiencies built into their system. Finally, in the early 90s, I read something in The Economist that pointed out the United States was the most productive nation in the world in terms of person hours per whatever you want to use as the metric, whether it's tons of steel or whether it's pounds of aluminum or computer chips or whatever. We actually had the competitive advantage in almost everything, including agriculture at that time. Now, there's some parts of the world, I think Thailand now is the most productive rice grower because they got the right climate and the soil and whatnot. But we are the most productive nation in the world and have been for the last century. Okay, we passed the British so far as that goes. However, the important thing here is to read the very beginning of this book. It says, "To live well, a nation must produce well." So this is a book that was written by actually a committee, but it was led by these three people. And I served on one of the committees that actually looked at the steel industry. And there's a section in there on the steel industry, so far as that goes. Another quote, which I thought I'd written down, but anyway. There's a guy, Paul Krugman, and I think I've asked you, oh, here it is, if anybody knows who Paul Krugman is before. He's an economist. He did all of his really good work here at MIT. He wrote some very good books that were understandable and correct principles. He then went to Stanford, which was when he won the Nobel Prize. And now I think he's back at Columbia or somewhere. Anyway, he's still around and he's still doing things. But he's an MIT product. And so here's Made in America. To live well, a nation must produce well. Paul Krugman used to say productivity isn't everything, but in the long run, it's nearly everything. And that's where I talked about nails and, it used to be, I actually have the plot here, which I showed you way ahead of time, of a little graph I made the year before on productivity of steel. Okay, so here's productivity of steel, a graph that I put together last year for this course. Just scratched it out one morning, and so we got hours per ton on a log scale versus time on a linear scale. It was very labor intensive back in the old days, and then the Bessemer process came along. We learned to melt steel before we basically either started with cast iron, or if we made wrought iron, we basically diffusion reduced it from the ore and ended up with a sponge, which we then had to forge by hand into wrought iron, okay, so which was steel basically, a lower carbon cast iron. And then Carnegie came along with economies of scale and built huge steel plants based on initially the Bessemer process, but later the open hearth. And then we came up in the 60s with the basic oxygen furnace, continuous casting, mini mills, which were smaller, a way to use a lot of scrap. And here we went from labor intensive in 1975, when I worked for Bethlehem Steel, it was 50-50 labor materials. Actually, it was 45-45, and they actually made a 10% profit. In the 1980s, it was 55-55, and they made a 10% loss. That's another story. Raw materials, energy intensive today, okay? That's what it takes to make steel. Doesn't take much labor. We're down to 20 minutes a ton, okay, per person ton, or whatever. Well, why do we have that? Let's talk just a little bit about what happened in some of the details of the steel industry. People asked me about that before, and I went through a little bit of it, but I didn't give you the whole story. I did find, I told you the story of Saugus Iron Works and the problem of they were running out of wood in England, and so in the 1620s they basically started an ironworks here, the first one in the United States, because we had a lot of forest. And they needed the energy, which came from wood. Well, this is something out of the Metals Handbook on casting. Development of foundry technology in the United States is the chapter, and here's a little plot of the Chesapeake Bay in the 1700s, and it shows you Northeast Forge in 1735 and Principal Forge, Furnace and Forge in 1724. In the 1700s, there were all kinds of forges around the Chesapeake Bay. Okay, this became the center of the iron industry in the 1700s, which was the beginning of the metals industry in the United States. Saugus failed in the first 10 or 20 years and went out of business. But eventually they did, because of the wood, and in this case, because of all the water power down in Virginia, if you know anything about the rivers, the Rappahannock and stuff. And you could eat clams for lunch. Okay, actually, not clams, but oysters. They used to feed oysters to the slaves and to the lower paid laborers because they were so plentiful. Rich people didn't eat oysters. Okay, that was poor people's food. Okay, nowadays you go try to purchase an oyster. I had an oyster yesterday in San Francisco. It cost me $3 a piece. Anyway. And then we talked about the nails. Well, let's talk about what happened in some of these processes. So the Bessemer converter came along, and what happened is you couldn't melt steel with a regular fire. You can stick a poker of steel or even cast iron in a hydrocarbon fire burning in air, and we make furnace tools. Okay, we make the hearth and stuff out of cast iron. Okay, it doesn't melt. But Bessemer came along, and basically what he did is he built a converter where you had the liquid iron here and you'd blow the air in, but the exhausting air would come out and it would sort of preheat the air coming in. So it was a very poor, crude way to preheat the incoming oxygen. If you preheat one of your oxygen or your fuel, you get a higher temperature flame. And he was able to, with a particular type of furnace design, he was able to blow air in and get this kind of open exchange, heat exchange here, and end up being able to melt steel. Now, that wasn't very efficient, but they came along with, and this is what Andrew Carnegie used, was the basic open hearth, or the open hearth furnace, where you just had a big furnace and you have a layer of liquid iron about 3 feet thick. And you start figuring out the density of that iron. We used open hearths from the 1880s to the 1970s. When everyone else was going to the basic oxygen furnace, U.S. Steel, being the conservative people they were in the 1970s, put in the world's last open hearth furnace at 450 tons, probably the world's largest steel furnace ever made. They were just going bigger and bigger in scale. Well, it turns out to do this and to preheat the air in a big furnace like this, first of all, it has to be a fairly shallow bath because you're still getting the reaction of burning the carbon out of the cast iron, which comes from your blast furnace. You blow the air in here, and the oxygen burns away the carbon, leaves behind an iron liquid that has less carbon in it, and you control it, the time of burning, get the carbon down to what you want, and then you can lift up this whole, it's about 1,000-ton furnace. If it's 450 tons of iron with refractory and the walls and everything else, you actually, some of these things would actually tip up. Pretty massive things. Some of them you would just tap out of a little hole. You basically build ceramic and then you put a little piece of dynamite in there, blow out the hole, and all this liquid iron comes rushing out. Pretty hard to stop. You basically have to have something to catch it. And if you don't, you have a mess. I remember one of my classmates one summer worked for Chaparral Steel, and so Harvey comes back and he tells the story that summer that the foreman in the melt shop was an hourly employee, this type of guy who maybe graduated from high school, but he was making a lot of money. When I worked at Bethlehem Steel, the foreman in the melt shop was an hourly worker who was probably making $40,000, $50,000 a year. I was making about $20,000 a year as an engineer. So the foreman in the melt shop, he had to turn out about 300 tons of steel every hour, and he was responsible for it. He didn't know a whole lot about it, but he was responsible for it, and he had about 30 years working in the steel industry, and he made more than almost, he didn't make as much as the plant manager, but he made more than most of the college professionals. Anyway, so the guy's sitting there in the control room, and the engineer comes in, he looks up at the gauges and he says, "Oh, you haven't tapped the heat. I want you to go ahead and tap the heat," which means out of this type of basic oxygen furnace down here, he means this whole thing is about a 500-ton vessel and a couple of 100 tons of steel, and it's on a trunnion, great big bearings, and you basically tip it over and pour it into a big ingot. It's on a big railroad track, and then you carry it away to cast it in the molds and stuff. Well, anyway, he comes in, this is in the 1970s, he looks up and he says, "Oh, you haven't cast the heat, I want you to go ahead and cast it." And the guy says, "But," and he says, "I don't care, I told you to cast it and do it." And he walks out. Well, the guy, hey, he's an hourly employee, he makes more than that guy, so he does what he's told. He taps it. Problem was, there was no railroad car there yet. That's why he hadn't tapped it. So he taps it right on the floor of the casting shop. Now, the floor of the casting shop is usually just dirt, but it takes about a week to clear that up, and $5 or $10 million. Okay, because you sort of now welded all your steel parts in your cast shop with this big puddle of 200 tons of molten steel, which solidifies. You have to wait for it to solidify, and then you have to go in there with oxygen lances and cut it up. Both of them lost their job. Okay, but the moral of the story is, have enough respect for that hourly employee and listen to what he means when he says "but." Okay, he may not be completely stupid. Anyway, the problem with the old open hearths is you had to preheat the air. So you had this basic open hearth, which could be a quarter the size of a football field, and then you'd have these two big buildings of 2 or 3 stories of brickwork, and it's brickwork in a big lattice. And initially, you'd fire this thing up about once every 2 or 3 years and run it for 2 or 3 years before you'd shut it down and replace the refractory. But you had to heat up the brickwork and stuff. The exhaust gases would go through this brickwork, preheating the bricks. Now, this brickwork might be half the size of a football field, or the size of a football field, all inside a chamber. And then the gases would go up the stack. But you're going to preheat these bricks. In the meantime, from about 12 hours before, you had preheated these bricks, and the air comes in, and that's how you preheat the air going in. And then you switch over every 12 hours, and you're just using the thermal mass of these bricks to contain the heat. Okay, so you're taking your waste heat going out to heat up bricks, and then you switch it over, and you have your air coming in, and those hot bricks are now heating up the thing. Fairly inefficient process. Took about a day to produce 300 tons of steel. And in the early 70s, even though in the late 1950s some Austrians had developed a process where they took pure oxygen and blew it through a lance onto the steel, and in 30 minutes they could burn all the carbon out with pure oxygen that took a full day. So there's about a factor of 50 in productivity. This shop has an area that's 1/4 the footprint of this shop. So everybody in the world, the Japanese and except U.S. Steel and Bethlehem Steel, others, they weren't, you know, they were about 10 or 15 years behind because they were used to doing things the traditional way. Anyway, so you know, and this thing actually is only filled about 10 feet deep, and it's about three stories tall. And when you actually blow the oxygen in there at supersonic velocity, or sonic, actually it is, well, it's not supersonic, but at sonic velocity, it's liquid oxygen. An oxygen company will build a plant right next to the steel mill to supply the liquid oxygen. So they do a refrigeration plant, whether it's Linde or Air Products. You'd have a company that would build a plant right next to your steel mill to be able to supply the liquid oxygen. And this whole thing turns into a froth that's about 2 or 3 stories tall of just molten steel and oxygen just reacting and burning rapidly. It's pretty dramatic to see it from a distance. When I was at Bethlehem Steel, one guy retired and then he decided to commit suicide, so he came back and jumped into the bath. You float very well on steel, by the way. They could see the body spread eagled on top of the bath. And in a case like that, what they do is they bury one ingot in the cemetery. Okay. The only problem with the steel is the phosphorus increases because we have a lot of phosphorus in us. Phosphorus is an impurity in steel, but anyway, so they had to degrade the steel a little bit. So you have a BOF converter, and then you take it and you may do argon bubbling to get even lower carbon. You could do degassing, where you actually pull a vacuum using this Venturi technique that was developed here at mechanical engineering at MIT in the 1940s. You can degas the steel and then you pour it into a ladle, and from there that's transported by the cranes and it goes into a tundish, which is stationary, which is just a holding vessel, and they control the rate of casting the steel in this little vibrating copper mold, which might be about 10 feet high, water-cooled copper, and the steel is coming out red hot. And you actually can bend it with rolls, turn it horizontal, and cut it off into big slabs, about 10 inches thick. Yeah?
So, with the pure oxygen, is it the fact that you're jetting the oxygen in there and there's so much application that...
And you got so much surface area between the gas and the liquid that you're just getting a very rapid reaction. First of all, there's no nitrogen around to mess things up. And you're just, the oxygen combines to carbon monoxide. And one of the reasons it's nice and dramatic is you get a carbon monoxide gas jet coming out of here that's about 10 or 20 feet tall. Okay, I mean, you don't stand right next to it. You kind of stand about 30 or 40 feet away. But it's pretty dramatic, and you can feel the radiant heat at 3,000 degrees Fahrenheit, okay, coming from this. But you're basically getting a froth, and you're getting huge amounts of surface area between your liquid and your solid, and just burning that carbon out of there. And it just, anyway, it's a little explosion, controlled explosion going on in there. It's a huge deflagration, yeah. No, it doesn't, until you get down to very low carbon. The thermodynamics are such that you can get down to about 0.05, about 500 parts per million carbon, before you will start to oxidize the iron. Now, the people who worked all that out, there's a guy named John Chipman here at MIT who was head of the materials department. And John Chipman, and after him, John Elliott, who was one of his students, and Tom King, who was the department head after John Chipman and was the department head when I was a freshman or an undergraduate. All the world's steelmaking technology, the chemistry of it, was developed here at MIT, okay, by John Chipman. I remember John Elliott said that when Nixon opened up China, and John Elliott in the late 70s was one of the first scientists to go over to China from the United States. And he visited one of the universities there, and they had a book written called Elliott and Gleiser. John Elliott and Molly Gleiser had written this book on thermochemistry for steelmaking. They had it enshrined in a glass case at the library. Because the Chinese didn't have, you know, Mao Zedong didn't allow them to purchase a lot of European things. Harold Larson's got a case of those things down in the basement, those volumes. He was a student with John Elliott at the time. We have a Chipman room, and most of the over half the chaired professorships in this department come out of the steel industry, in part because of John Chipman. Back in the 1920s and 1930s and 1940s, it was sort of a crapshoot to get the right chemistry for the steel. You kind of melt it and put it in the basic basic open hearth furnace, and hope through a kind of trial and error experiments that you get the right chemistry. But you could end up with 300 tons of the wrong chemistry steel, which you got to downgrade or even remelt. Well, John Chipman came along, and using the principles of physical chemistry, he was a physical chemist from Georgia Tech. And he came up here and he applied those same principles of physical chemistry to high temperature physical chemistry, not aqueous chemistry, which is what the chemists were doing in water baths. He basically applied the same principles to high temperature glass slag baths and steel and stuff, and figuring out how the elements partition between the slag phase and the metal phase. And so now we can hit those chemistries right on. You get one bad chemistry out of 100 heats today, whereas in the old days you probably get 10, 20, 30% bad heats. So that's one of the things about productivity, okay? If you go in the Chipman room, you'll see, Benjamin Fairless Works Award, okay? World's largest steel mill at the time was the Fairless Works of U.S. Steel. Anyway, so they take that, and then there's lots of metallurgy that goes into, this is the tundish, where this stuff is flowing around and it's coming down and it's going, these are the water-cooled copper molds, and you got solid flux, liquid flux, you got a vibrating copper wall, it's contracting, and you actually have, the molten zone is here, you're actually using hot solidified steel that's being supported by rolls, and sometimes you'll have a breakout. This little continuous caster you see here is about 10 or 12 stories tall. It's a pretty good sized building. You want to build a continuous caster like this today, probably about $2 billion, okay? But if you have a breakout, you're going to drop your whole tundish right onto the floor, just like they did at Copper Weld, but the guy did it sort of intentionally because he was irritated with the jerk engineer, okay? And there's all kinds of microchemistry that's going along in here, where you get solidification in dendrites, and you get pushing of the inclusions. And anyway, there's a tremendous amount of technology that's been developed in the last 50, 60 years, but most of it was developed between the 1940s and 1980s. There really hasn't, once they lost their productivity in the steel industry, they started closing the research labs, and steel research did go down. There weren't any jobs. Now they're coming back, and they want to hire students, but there's no students. Everybody's working on semiconductors, yeah.
Why do you want your copper mold to be vibrating?
Because you don't want it to stick to the walls, because you're trying to get it to move through there. And so you vibrate it. You don't want it, basically you don't want it to weld to the copper wall, and you want to reduce the wear on the copper. That copper's got to last for about 3 or 4 years before the shutdown. I mean, the Japanese have run continuous casters for well over a year without shutting them down. Okay, so you run 24/7 for over a year, and these things have to be fairly robust. Okay, and so vibration is one of the things that helps.
But isn't there a risk of the steel falling down the caster? There's a lot of space between
the
rolls.
Well, hopefully you've got these water-cooled copper molds. This could be 10 or 20 feet high, and you're going to have built up a skin on here that's going to be 1/2 inch or 2 inches thick, depending on your casting speed. Okay, the actual only contact is just up in here. Hopefully it's cooling away, and you just got radiational cooling here from the water-cooled copper that's helping grow that skin. And one of the reasons you can bend this thing so easily is because part of that, the first part, it's basically got a liquid core. And if you're not careful about the radius of curvature and the speed of casting, you can have a breakout, and all that liquid steel falls down through everything else, and that's probably a $100 million loss. Okay, so they got a lot of control algorithms and everything else. They got a lot of incentive to run it as fast as possible, but not too fast. Okay? A lot of technology, a lot of experience there. Breakouts are not very common. There's probably not more than one breakout in the world every year or two today. When they first started doing it in the 1960s, a lot of people said, oh no, that process will never work. Okay? Well, some people said, hey, going from 65% yield in, of pounds of steel produced per 100 pounds, cast, to 97% is a big enough increase in profitability that they were willing to bite the bullet and do it. American steel companies, no, they were too conservative. Board of directors were not willing to take a risk. It was people who were willing to take a risk, but some of those people were in foreign countries where the government was backing up their risk. Okay? So it wasn't exact. It's sort of like the whole Airbus Boeing type of controversy today of how much is the government supporting both of them. In the United States, well, we don't support Boeing. You know how much money Boeing gets in defense contracts every year? And you don't think that they're doing some of that as a way to support things? What about the new Air Force tanker program, which basically went to a consortium that included Airbus on the first bid, but then all the Boeing people go in there and start yelling to their congressmen, and they just force the Air Force to reopen the bid. And guess who won that time? Boeing. Okay. Now Airbus is pretty much directly, subsidized, and they're always having fights with each other about, oh, you're illegally subsidizing your aircraft industry. It's a tremendous export industry. What's Boeing today? $40–50 billion a year worth of exports, and fairly profitable in general. Yeah.
They also got space contracts too all the time.
Yeah, space. Half of Boeing is government contracts. Okay. So, yeah, we don't really subsidize in the same way. We just subsidize in a different way. But our subsidy is okay, we say. And the Europeans say, no, it's not. So, anyway, these are some of the externalities, right? So, it happens in lots of industries. And then, it was a real problem for the American steel industry in the 1980s because everyone had convinced Congress that the Japanese were not dumping steel, and then the Romanians, and then the Koreans in the United States, and now the Chinese, okay? They've been fighting this for 40 years. It turns out that, yes, the American steel industries were losing a tremendous amount of money in the 1980s. But the reason I showed you these plots before, the productivity had doubled. The consumption was constant, the employment went down. Well, that was because of productivity. They went to BOFs from open hearths, they went to continuous casting, they did a number of other things, okay? They built mini mills, and mini mills could use 100% scrap. In the old days, before the mini mills, let me turn it upside down, they had to use 70% virgin iron ore to make the steel from the cast iron, and only 30% scrap in that BOF. Well, an electric furnace can make the steel out of 100% scrap, and you can use John Chipman's principles to purify the scrap to get the chemistry you want, which is a lot harder in aluminum, because it is your question about how much can you burn out all this carbon before you start burning away iron. Well, if you start burning away iron, you're going all the way back to iron ore, and that's not what you want to do, right? It's a lot of wasted energy to go full circle. Well, in aluminum, you'll burn up the aluminum before you burn out the copper and these other things. In steel, you can basically burn out a lot of these things. Certain things you can't burn out. Bismuth out of steel. You get bismuth impurity in steel, and it goes to the grain boundaries and produces a brittle product. And and everybody, 15 years ago, people were trying to get lead out of solder, and they're still trying to get lead out of solder. And I go to these conferences and they say, oh, well, we've developed this bismuth alloy. I say, that's great. So you're going to start putting a number of pounds of bismuth in every automobile, which means we will no longer be able to recycle steel automobiles. That was dead on arrival. But these metallurgists who were working on solder, they didn't know anything about steel making, and they didn't realize that nobody was going to put bismuth alloys into the soldering on an automobile, because you can't, you're gonna now have to go out there and separate the scrap. Okay, you can't just shred up the automobile and dump it into the furnace. You gotta have to separate it out. Now we separate out some things. We take out the airbag explosive because that has killed people in some of the steel mills when they're shredding. You know, shredding it and all of a sudden, pow! You got this explosive and you got this piece of shrapnel that goes right through someone's arm or something. So they do go in and do some things. But you can't start ripping all the wires out of that thing. You couldn't afford to recycle the steel. Well, what happened in the 1970s is people like Gordon Ford and Ken Iverson realized you could buy scrap steel at $100 a ton on the open market in the world. There are millions of tons out there, okay? Cast iron cost $200 a ton. So you had a 50% advantage. You had a $100 a ton advantage on something that's sold for $400 a ton. You had a 25% cost advantage to use 100% scrap, except the quality of the scrap was not very good because it had all these alloying elements. And about the only thing they could make was reinforcing bar, concrete, steel concrete reinforcing bar. Just has to have 60,000 strength and be the right diameter, and that's about all. It doesn't have to have toughness requirements because, let's face it, the concrete has no toughness, so you put the steel in it, it's tougher than it was, okay? So you could make rebar, but rebar was the garden variety, low quality stuff. And when I was Bethlehem Steel, the manager, we don't care about mini mills. Well, this is what Clayton Christensen made his name for at Harvard Business School on the innovator's dilemma. Okay, here you have these little mini mills, and one of his sections, one of his 3 examples is steel mills, steel technology. My daughter worked on researching things for him one summer, and I'm a reference in there on what it costs to build a steel mill. Rebecca came home and said, "Dad, Clayton wants me to find out what it costs to build a steel mill, and I can't find it anywhere." Well, this was like 1995, and no one had built a steel mill since Bethlehem Steel in 1965. It had only been countries that had built it, and so it was all mixed in with the country, the government finance and everything else. Well, it turns out about a year before, I'd been sitting in a Saginaw, Michigan airport with one of my graduate students, and we'd sketched out, I just sketched out on a piece of paper the approximate cost of an integrated steel mill, a mini mill, and a micro mill, okay? And a mini mill you could build for like $100 million. A integrated steel mill was $15 billion was my estimate. It had cost Bethlehem Steel in 1965 $5 billion. That was their whole year's gross product, okay? And they almost went bankrupt. But by the time they hired me, it was the most profitable year ever. That's why they could afford to hire me, right? But they almost went bankrupt in the previous 6 or 7 years. No one could take on a $5 billion investment back in the 1960s. That's like Intel taking on a $15 billion investment today, or Boeing a $15 or $20 billion investment. These companies are betting the farm on these, building a new 787 Dreamliner or a new computer fab and things. Other countries, it's the whole country. And there has never been an integrated steel mill built since Bethlehem Steel Burns Harbor by a company. Been plenty of integrated steel plants built, but by countries doing the financial backing. No private investment eating a 15 or today probably a 20 or $30 billion investment for an integrated steel plant. Anyway, we're going to run out of time, but so what they did at Chaparral Steel, Gordon Ford's a graduate of this department. He's a Canadian. He's retired in British Columbia now, but these guys, they sent their own employees out with sales every now and then. If you were an employee at Chaparral, you had to go spend 1 week a year with the salesman in the field to find out what the customer wanted. Hey, what a unique thing. And they found out that the smallest diameter rebar, 3/8 of an inch, got like a 20 or 30% premium because you could only go so fast through the rolling mill. So here is what they did. First they came back and said, we're going to roll faster. We're going to sell more 3/8 inch. We're going to take over the 3/8 inch rebar market because there's more profit there. So they tried to go faster. Well, this stuff is going through there at 60 miles an hour. Okay? And if you go faster, you get instabilities, and all of a sudden you got hot band steel that breaks and goes whipping around. And if someone's there, cut your arm right off. My second child, my oldest daughter Rebecca, was born in the hospital in Bethlehem, Pennsylvania. Beautiful hospital, because they sent maimed steel workers down there every day. Okay? Just cut your arms right off, okay? Anyway, so they tried to speed it up for a while, and finally they said, no, we're doing it the wrong way. We shouldn't try to speed it up, we should try to slow it down. And what they did, they slowed it down. And here it's coming into the rolling stand as 1 bar, and it's coming out as 2 bars. They split it in 2. They had to go slower to do it, but they got twice the productivity out, right? At a slower rate, which is like a 50%. Well, hey, they did that once. They decided they could do that again. And here you see, oops, you don't see anything. You see 2 bars coming in, and you look down here, and you see 4 bars coming out. They did it twice. And so they're running this mill slower, but they're getting 4 times as much product through. So they took over the 3/8 inch rebar market. Yep.
Was the quality maintained?
Yep. In fact, I'll tell you about that tomorrow. The quality actually went up. Okay? And that was another benefit. But they really did that, prove that in an I-beams, and that's the rest of that story. Okay?
What was the timeline? How long did it take them to show from
Less than a year.
fast to
Less than a year. You can read about it, actually not in this book, but there's another book that I actually was involved in reviewing Chaparral Steel's product development stuff with the guy Steve Wheelwright at Harvard Business School. So you can read about it if you're really interested. It was written up.